Yes, so I first of all would like to thank you very much, Luigi, for the opportunity of being here. I'm really honored to be able to be here and talk a little bit with Mario. Mario, first of all, would like to talk about Brazil community. So as probably many of you know, Mario went to Brazil many times and has several students in Brazil. So he planted many seeds in our network community. And he was very important as well as in Italy to build up the community, the research community that we have now there. And Mario was my teacher. My first course at UCLA was taught by Mario, Communication Networks. And Mario, we wrote part of my dissertation with Mario. And my first project was done with Mario. And since then, we developed a very friendly relationship. He was my friend. So Mario is deep in my heart. He always be, and to all many Brazilians, he touched there. So thank you very much for being here. And I choose network measurement so for two things. First, Luigi asked to do something new, and so this is ongoing research. So none of those things that I'm going to talk about have been published, except very recent, a couple of weeks ago. It's a Brazilian conference. And also because, so this is a collaboration between the two faculty members of my department, Daniel and Rosa, who is here, and PhD students, and UMass, Don Tosley, probably most of you know, and one of his PhD students. So it's a collaboration project, and as Maggie was able to mention, one main thing about Mario is connecting people. So this is research that connects many people together. And the motivation for the talk is in the very beginning. I'm from the old people at UCLA. And at that time, ARPANET, when I was a student, was the network measurement center. So I heard a lot of stories from Len, from Mario about collecting measurements and trying to learn what's going on from the networking. And so that's why I chose this topic. So as you all know, as the network expands, home networks are increasingly complex. So in fact, with some of the measurements you have, I was astonished that even in Brazil, a house have more than 13 or 14 devices connect to a network in the average. That's an interior of the country. So I was very shocked by that. See, so it's home networks have become increasingly complex. But we don't know much still about this recent environment. And most measurements that have been done, they're collected the routers in the, what some people call the edge, but in the edge for the ISP, I mean. So they aggregate a lot of traffic. They have to look to packet headers to separate flows and thousands of homes. And so it's a really tough task. So the issue, so how to do a detailed analysis for that, that's maybe very costly, private issue, et cetera, et cetera. So in this talk, I'm going to focus on very lightweight measurements, that performance at the home gateway. So our measurement device, it's that the gateway that is inside the home. And of course, data analysis. And why the home routers? Because they are the conduit for the network environment, for the home network environment. So it becomes an ideal place to implement all the measurement functionalities. So in this project, so it's a collaboration with US and mid-sized US ISP in Brazil. So he's been very nice, this ISP, because he opened up a bunch of their database, and a startup that from students that came up from the university, from my lab, and incubated at the university. So they are doing all the software measurement, etc. So as a Brazilian, I talked a lot. So I decided to talk about 3 issues, but probably time may not allow. In fact, the only time I couldn't talk a lot was when I was biking with Mario, because then I didn't have the breath to keep up biking and talking at the same time. So, but if I can cover the 3, okay. If not, I stopped in none of them. So the first issue I'm going to touch is about to investigate denial of services detection from the home router, exactly at the point it go. Then try to touch a point of access quality of experience and from residential users, from time series, all the time series are collected. And if times allow me, I'm gonna also try to talk about some of the traffic that flows from the home network and try to understand some of the patterns in the traffic. So let's start for the first saying that what are the measurement we're there. So as I said, as we partnership with the ISP and a startup, so the startup installed the measurement software in the home routers, and it collects a bunch of measurements from the home and to another computer that's installed in the ISP premises, and then they shipped us to the university. So it's a data collection campaign, and we are working with approximately 4,000 homes collecting data, and that's growing. Right now we have the software installed in 15,000 homes of the ISP, but we are keeping 4,000 homes for study. One of the key issues, but what are we collecting first? I'm going to talk about what we collect. We collect byte counts from the router. Routers are very inexpensive routers that we use. It's not expensive routers or anything, so they are put there by put in the homes by the ISP. So they have very limited capability. So it's important that we don't take too much CPU of the router. So we use byte counts and packet counts, and for download, upload traffic, we don't look at the packet headers. So we do loss measurements, latency, also other stuff like processor load, and recently we collect a lot of data from the Wi-Fi networking, which I'm not going to talk about that. And we measure it at every 1 minute, and we have already changed the software to measure every second, but now I'm going to talk about the 1 minute time scale. Our goal is to do this data analysis using many time series that we collect, and we applied unsupervised learning techniques for trying to learn some spatial temporal patterns and to try to identify an anomaly in traffic that we could interpret. And try to identify statistical changes in data traffic and also in the quality of service measures that we collect, and try to relate with some of the codes inside the network, and perhaps new perspective to understand the behavior of the domestic home. Okay, so I'm going to talk about the first issue, and the topic I name as lightweight approach for DDoS detection at home gateways. And what is the objective here? We all know that DDoS attacks are very prevalent. There are many sorts of information and say what's the damage they cause. And even recently, before coming here, there was a report that's saying, despite of the law enforcement effort, DDoS attacks remains a real threat for business. And that's very recent from May 21 report. So how can we detect the problem and react very fast and detect where the problem is start? So our approach is to think simplicity. So methodology has to be simple enough to be able to scale. Locality, so we try to detect problem very close to the source. Efficient, fast attack reaction or identification and reaction. And minimalism, so we collect minimum amount of information at the home routers. So we avoid interference in performance and invade the user privacy, which is also, of course, a concern to us. And question, with minimal information, it's possible and it's feasible to detect those attacks in an extremely lightweight fashion without relying on information from packet headers. So what are the methodology? We went first to the approach of machine learning and training classifiers, but I should tell that like Len was saying in the first talk, you should understand the basics. Don't use machine learning as a black box or anything like that. What you have to understand what's inside. But that's good to attract the students. If you say that you're going to use machine learning, they get all excited. But then you say that they have to learn queuing theory and et cetera, but they are already in the project, so they remain. But we trained several classifiers and making use of workload data for almost 2,000 homes and for 12 days, but we have much more data. So numbers of I'm presenting are days from March, April 2019, so that's very recently. And that was used a baseline. Then in the lab, we got the real code of those attacks. We take that, so the attacks, they vary some parameters. They are similar to each other, have very similarity, so we get the mains types of attacks from Mirai and Bashline, malware, and also we vary some of not only the existing attacks, so we vary some parameters to change, to get, let's say, a new attack. And we do that in the lab with many different Wi-Fi conditions, etc. And we combine to take the time series of that we collect from home. So we also inject real traffic and the attack traffic in the lab and analyze the difference in the time series analysis. So this picture gives you an idea what's going on very briefly. So the blue was let's say, the normal traffic. And again, it's thousands of time series that we collect from homes for the day at every minute. And the red are the attacks that you randomly inject in different parts of the time series and different users as well. So we vary the length of the attack and everything. And we have a sliding window, a small sliding window that moves that way and tries all the time to identify some anomalous behavior. So this problem is not easy. Again, we used machine learning techniques that's to try to identify some patterns and see what is important, what are key parameters that are important. And so just to give a brief idea, with a bottleneck like Mirai and Bashlight with different parameters that we are able to have accuracy of 3 digits, 39, precisions 2 digits, and recall and F1 score also very good with the training. And again, our main purpose is to understand the basic, what's going on, why can we detect that with those classifiers, what is important, what's not. And also consider different machine learning models for that, do cross-validation, all the user stuff, and we try to identify and see what's important in the time seriously. And again, I emphasize 2 points. We did not use packet headers, and we consider also the space-temporal correlation. This is the detection rate for one home. But now we can combine what we learned from different routers at the same time. So if you do that, and it makes it a decision problem, use map criterion, maximal posteriority criterion. We are able to come up with a formula that gives you the probability. As you detect in more homes, increase drastically the probability of detecting an attack with very little homes in the ISP network. So currently, and again, we have a formula for that, and currently we are deploying that on the wild and to collect the measurements in the wild. So that's the state of that. And the other topic in this, let's say this measurement effort, you can say, oh, it's a completely different topic. In fact, it's not. It's very interrelated with the other topic. So we approach, say, looking just at time series of loss rate from the home router. Can you infer something about the experience of the user inside home? As Len pointed out in the first talk, loss is not the only thing. Of course, as many, like TCP reacted to losses, but what we're interested here is loss affects the quality of experience of, and how can it affect the quality of experience in the home. So this is a change point detection problem that we work with. We want to identify what are the points that the losses affect badly or not, or I don't say badly, but affect in terms of the user perception, the quality of his experience, of her experience, and we just time series of losses. Of course, we are moving to latency and other time series as well. And where are the points that you change? You see some statistical change in time series. So the objective is automatically problem identification, and perhaps with the time series, maybe congestion, or equipment problems and attacks, whatever, and identify those temporal patterns. And the issue is the quality of experience affected? Can we correlate the quality of just packet losses in that sense, and later latency, etc., with some ISP calls to home? And again, for this problem, we use unsupervised learning techniques. And again, I said you matched with change detection problem. It's a problem that you see a change point detection problem in time series. You get hundreds of reference, perhaps thousands of reference. And we make use also of spatial time correlations using the ISP network topology that the ISP gives to us. That's also some tricky to get all this data from the ISP. ISPs, sometimes they don't know their topology, but that was very good. They have very well structured ISP. And we try to locate the root cause and mesh the QoS. Again, we have 2,400 homes that we work with it. That's we from another period, last year, the end of last year. In this report that I'm showing here, we use just packet losses and use time series for training, etc. And you use a hidden Markov model, as your basic algorithm to try to locate the detection and change of these statistics, together with a recursive filter to try to remove, let's say, spikes, etc. At the end, we use a voting mechanism with the spatial to try to correlate the different network problems that you detect from home to some issue. And this picture, it's already the output of the hidden Markov model, and the red is when the network is bad. You see, how do you do that? I don't have time to go into this issue, but let's say the blue are the nice periods of packet losses, and the red, I say, well, we'll detect some bad statistical change, so that creates a problem. So this is part, just to illustrate this talk, this is part of the, let's say, the topology of the network, and this is a real experiment. So we point at some point in time that there may be problems that is in the red parts of the network. The green are okay, so you should look into those parts here. So then they change one of the equipment in the nodes. The nodes are equipment, could be a router or could be just a switch. So they change the equipment, and you can see that the measurements now came to green. There are still problems that they fixed later. So what we did, so first of all, it's a tool that in real time can send a warning to the operator saying, well, we may have some problems there. And now the question is, are those problems affecting the client? So, and that's just to illustrate the time series after and before and after. They changed the equipment. There was a problem in the equipment. And so the question is now, can you relate that to real phone calls complaining about the service? So ISP gave us this data. It was not easy because the data was not, we have to do some cleaning of the data, but pretty good, they're pretty good. And if we have measurements equipment or home routers that are making measurements at some node where the call went to that region, we're able to identify 95% of the phone calls. So that means that we can ahead of time tell that there will be a problem, it's in affecting your user. But you don't need measurements equipment in all nodes. So if you have a scattered measurement equipment, which is the router, the home router, etc., you can correlate with the voting mechanism in a tree and then get up to 89 in these experiments of the phone calls. You could identify that there was a problem. Okay, so that was the second issue, and we are now studying some of the relationship with attacks, the DDoS attacks, etc., because we are all analyzing, it's a bunch of time series, thousands of time series. Okay, so since we collect traffic and see anomaly behavior, and can we learn something else from the traffic we collect? So that's the third issue. So we try to understand some of the characteristics of the traffic that are generated by the home users and how to try to extract meaningful information and patterns. Again, this is more tricky to explain in 3 minutes or 2 minutes, so I'm just going to go give you 1 minute. 2 minutes? Okay, 2 minutes. 1 minute because I want to say something at the end. And the methodology. So you use a perfect method, which is used in other areas. It's just a projection method, but has some advantage. And from that, we lever on tensor for clustering. And so perfect, it simplifies enormously the task of multivariable time series for clustering. And I'm going to jump. This is patterns already that we identify. Let's say they have 5 clusters here from user patterns, and this is one class of users. They are used more, let's say, at the end of the afternoon to the night. There are other users that use much less the network, and in fact, it was very good for clustering. And one interesting thing to finish this 1 minute is that there was, after a holiday in Brazil, we are able to identify some very change in this pattern behavior, a very big change in the pattern behavior that is in one of the curves at the end. And we say, that was the day, we didn't know the day was that. Then I went to say, what happened in this day? Why is it so different? That was the day just after the holiday when there was a problem in Brazil. One of the guys running for president, there was a tentative in his life. He was almost killed in this tentative. So that probably generated a lot of interest by the internet. And so we identified this method at that point. Anyhow, so I'm going to skip that. And just to summarize, so we can learn a lot from the edge. So that with minimal information. So we collect only byte counts and packet counts and losses, etc. So we can detect DDoS attacks, and seems we have identified problems and also have lots of traffics that profiles and patterns that we can identify from home. I will finish by a picture that I like the most. That is something that nobody mentioned here. Mario was very good in caipirinha lifting. So this is a proof of that. And usually go, one place that we like to go is to Academy of Cachaça. Cachaça was the drink that made of caipirinha, and that's a very scholarly place, Academy of Cachaça. So I have very nice technical discussion while doing caipirinha lift. So Mario, you are in our hearts. You live forever in my heart, in the heart of my students and their students on. We love you in Brazil. Thank you very much.